Howdy y'all. This is notes 1.3. This is the explicit equation and its column. So we're going to learn another equation we can write, like how we did yesterday. We learned about the recursive, and today we're going to learn about the explicit. There is quite a bit to write, so you will have to pause the video quite a bit, but I'm going to get into it so that we're not taking 600 years to make this video. So I see that we start with this 7, so I'm going to start with that 7 as we go down. And then I see that we go 7, 4, 1 in our dot column. So I am minusing 3 as I go. And what I'm going to do here is then I'm going to write my recursive equation, which always starts with f of n equals f of n minus 1. And we are minusing 3 as we go down the table here. Given that we started with f of, well, in this case we started with 0, so I got f of 0 equals that 7 that we have. Okay, so that's from the previous video. This next bit is where it's going to start getting crazy. So I have 7 and I'm minusing 3, but if we think about our table as we go down, that would be a lot of minusing 3's we would have to write. Like, we would have to write more and more each time. So instead, the explicit column helps us, and so that we don't have to write minus 3 that many times, and we can shrink it down. So in this case, it's going to be 7 minus 3. Now, minus 3, that means minus 6, right? There's 2 of these. So what I can do is I can do times 2. And if I do that, I get that 6 again. I repeat that for the row above, and again there was only one time we were minusing this 3, so I'm going to put times 1. And even though this is just a 7, we have to keep that pattern going, so we have 7 minus 3 again, but in this case we didn't minus 0 any times. Okay, and what I want you to notice is how these blue parentheses, they match that n column that we have going on here. Okay, now the 7 stayed the same, the minusing 3 stays the same, but those parentheses, those change, and that's going to be important for when we write on our explicit. And our explicit is always going to start just like a recursive with f of n equals. However, we won't have the rest of this. From here, we start writing out what we see in our explicit. We have that 7 that's repeated the whole time. We have that minus 3 that's there. But I can't write a number inside of my parentheses here because that number is continuously changing. So instead, we put the variable n, okay? Now, what happens if we have the same f of n, right, the same dot section, but we start with a time 3 instead? Well, everything about it in the table for the recursive is going to stay the same. Okay, nothing's really going to be changing, except for when we write out our recursive equation. Once again, we will still have f of n equals f of n minus 1. We are still subtracting 3. We are starting with, this time, f of 3 equals 7. Okay, so this time instead of a 0, right, we had a 3. That's what's changed. So that's how the recursive changes when our time changes. With an explicit, it's going to be a little bit different. So the explicit column, once again, is going to be the same as the explicit column up here. We are minusing 3 the whole time. And in this bottom row, we multiply by 2 because we minus 3 twice. We multiply by 1 because we minus 3 the one time. And then we multiply by 0 because we minus 3 no times. However, when I look at my n column and my parentheses, they are not the same. This is a 3, this is a 0. This is a 4, this is a 1, this is a 5, this is a 2. So over on the side here, I actually have that written out. So we had 0, 1, 2, right? That's what was in our parentheses. But in our n column, we have 3, 4, and 5, okay? So what can we do mathematically to 3 so we can get a 0? That is the same as 4 to get to 1. That's the same as 5 and getting to equaling 2. Well, what we can do is we can subtract 3. 3 minus 3 gives us that 0 that we need, because we're trying to turn this, even though we started with 3, we're trying to make our time 0 happen, because that's what's happening in the explicit is time 0. So I have to make this 3 into a time 0. Whereas this one was already a time 0, it already matched, so I didn't have to make anything happen. We were good to go. But in this case, we have to minus 3. And that minus 3 works for the 4. 4 minus 3 is 1. 5 minus 3 is 2. So I minus my 3 for my n inside of the parentheses this time, because I didn't start with a time 0, I started with a time 3. So we got f of n equals 7 minus 3. We still have regular parentheses n, but not just an n, because we didn't start with a 0. We have to do minus 3 because we started with time 3 instead. All right, so in what's very important about arithmetic equations, which is what these are because we were subtracting, they use what I like to call regular sized n's, or n, that we multiply. Okay, right? Regular sized n, and we multiplied it, okay? Now let's move on to a common ratio. So in a common ratio with geometrics, right? I'll start it out. We have this 2 that we're doing, and I see that we are multiplying by 3 as we go down, so filling it out like yesterday. And our recursive is going to go f of n equals f of n minus 1 times 3. 3? That's a terrible 3. Let's try that again, because that's looking like a backward C. Times 3 given f of, well, in this case, we started with a times 0, so I'm going to have times 0, but we started with 2 dots, so there's that. The explicit's going to be a little bit different, right? Because we can't multiply if we're already multiplying for how we extend. So we are going to use 2 times 3, and this is like a warm-up we did in class, exponent 2, because you can change 3 times 3 into 3 to the power of 2. And we can do the same thing all the way up. So I'm just going to do this to save some time. Now, we only had the 1 here. Here we had none, so I would put 0. My parentheses in blue is matching up with my n column, so that's good. We don't have to do some extra step here. So therefore, the explicit, just like before, right, starts with f of n equals, but this time we have those 2's going all the way up. Those stay the same. We have the times 3 going up because that's staying the same. However, it's not going to be a regular sized n. It's going to be an exponent sized n. And we only use the n because we already are at time 0. We don't have to make time 0 happen. So let's see what happens with this same problem, but this time we don't start with time 0. Let's say we have a time machine and we were able to go backwards in time and start at time -3. So this table is going to be built the same as before, right? We're multiplying by 3 as we go down, so that's nice, right? The recursive is f of n equals f of n minus 1. We're times in 3 here. And again, this is a video, so you can stop and pause and copy stuff down, and then you can listen. I'm going fast to save us precious YouTube watching time. This time, though, we are starting with -3. So I have f of -3 equals, that's other starting number, our 2 dots. All right. But with the explicit, right, once again, we are having 2 all the way down. We are multiplying that 3 technically all the way down. However, starting at the bottom, we multiplied that 3 twice. We multiplied this 3 once. We didn't multiply any 3's in the top row, so I'm going to put 0. Okay, but you know, this -3 isn't matching up this 0. This -2 isn't matching with the 1, and this -1 is not matching with the 2. So over here on the side, this is just works for you to see what we do. We have to turn -3 into a 0, a -2 into a 1, and a -1 into a 3. Well, the only thing we can do is add 3, right? -3 plus 3 is 0. -2 plus 3 is 1. -1 plus 3 is 2. So that means all my n's, I'm adding 3 to make it match up with that first times 0. Because again, we didn't have times 0, so we need to make times 0 so that these match. Or work out, I should say, would probably be the better way to say that. So we get f of n equals, we still got that 2 times 3. This time we have exponent n, and not just n, but n plus 3, because we did not start with the times 0. We need to make that times 0. All right, so if you need to rewatch those last 4 examples, 100%, please do. Re-listen to it. But now we're going to set up our own table. So we got day 1, we got 5 dots, and we have a common difference of 3. So we're using D for days, and then we're going to use f of D here, right? So we started with day 1. So that means we're going to have day 2 and day 3 next. We started off with 5 dots, all right? And we have a common difference of 3. So this means this is arithmetic. And because this is a positive 3, that means we are going to be adding 3 as we go down, okay? So you would extend your table right? And I'm abbreviating because, well, that's just how I roll. So if I'm adding 3, that means this would be 8, this would be 11. And if I made my table all the way through, and I'm going to do this relatively fast because I don't want to waste a lot of your time. This is adding 3, this is adding 3 twice. Here we're adding 3 all the way down in the explicit side of things. And we are going to multiply by 0 here, multiply by 1, multiply by 2. I'm not going to write the recursive this time, I'm just going to write the explicit. So the explicit in this one is going to go f of n equals 5 plus 3 n, and then I didn't start with a times 0, so to turn 1 into a 0, subtract 1. Okay. Same time, this time we're doing days again, so I'll use a D. That's fine, it doesn't really matter what letter we use. And we got the recursive and we got the explicit. I'm shorthanding more because I'm running out of space. We start with day 1. After day 1 would be 2 and 3. Once again, we are starting with the 5 dots. But this time we are using a ratio, so that's geometric, of 3. And if it's geometric, that means we multiply. Okay, so we would have 15 and 45. That's what happens when we multiply these. So we got that 5 that's going all the way down everywhere. In my recursive, it's times 3 and then times 3 twice. So in my explicit, That means I'm going to have at the bottom here an exponent of 2, an exponent of 1 for the middle, an exponent of 0 for the top. From here, we write the explicit again. I'm only going to write that one. And it's going to be 5 times 3 exponent n. And we didn't have a 0 here, so I have to make 1 into a 0 by subtracting 1. Okay? So now we want to use the explicit to find some numbers. So in this one, it's find -5. Sorry, my alarm was going off on my watch and I had nothing to stop it. All right, so we have a -5 here. So what I'm going to do is replace those x's with -5. Everything else stayed the same. Notice how I rewrote it so that everything stayed the same. Now here, I can't do much with this, so I'm going to kind of leave this friend alone. But on this side, I can do some stuff. I got -5 plus 1, so now I have 7 minus 3 times -4. And then I have -4 times this -3, which is 12. And now I get 19. So really, I'm going to bring this friend down. F of -5 is 19, although now it doesn't look like a 19. Now it's a 19. Let's do the same thing with this geometric one. We have f of x equals 3 times 2 to the exponent x. Find f of 4. So this 4 we're going to replace here and in this little exponent. Everything else about this, though, is staying the same. The only thing that changed was those x's. Well, I can't do anything with this friend, so I'm going to leave him alone. We got 3 times 2 to the exponent 4 is 16. And 3 times 16 is, mental math here. We got 8, carry the 1, 48. So bring this down. F of 4 equals 48. All right, y'all, that's the end of this video. Have a great day.